recommend using a probe like SafeVol or optical crashing your secret number or like without doing it.
If you actually do use this, you'll take other questions.
One last thing about links is that you should use the way you compare your because extremely important for information.
Yes, this will be getting on this show as the artifact is lesson.
So you want to minimize your shrink as much as possible because the Z shrink is greater than epsilon shrink during these sessions. So bear that in mind and be prepared to present your data as a post-processing system.
Okay, so we talked through this whole talk and we haven't really mentioned the word bias too much, but I hope that you realize that the things that we've been doing, the concepts we've been describing are to avoid bias. And one of the ways you can get into bias is where you look. And so we really want to stress systematic random sampling. And the idea that one histological section is only going to tell you about that one histological section and not the whole region.
Right, you want to be representative of the whole region itself, not the way that you're looking, but the answer that you're getting. And so you need to have the whole region available for sampling in order to ensure that any changes that may be happening in different locations are observed.
So all the codes we've recommended, you can only use systematic random sampling, and that's a big advantage too, because you can get a good snapshot, a good estimate of what's going on by counting surprisingly few events.
And so that's how you achieve some efficiency for your quantifications. And then you obtain this lack of bias by achieving precise.
Yes, this whole concept of isotropy that we talked about, look through the webinar and look at those summary slides. Those are going to be your take-home messages for when you're trying to estimate number or length or surface or volume. That's going to let you know how you're going to assure isotropy and whether you use a thick or thin section.
Yep, every aspect of your feature has an equal opportunity of being visited by your probe. And that's really what we mean by isotropy. All positions in your structure have the same likelihood of being sampled. We're going to say that sampling ensures that your estimation is representative and precise, and that we're going to encourage you to choose a probe that's efficient and easy to implement in order to obtain that unbiased quantitative information that you're looking for.
That was the criteria we used for these probes that we recommended. And as we went through this talk, I hope that this idea of behind stereology to do more or less well also came up.
Right, but do more or less well does not mean the incorrect answer. So let's just hark back to what you gain by thinking about the answer you want during your experimental design, choosing stereology over a method like image DA or something like that, where you're going to use an image analysis program to count cell profiles. Cell profiles, because it doesn't represent the unique point of your cell, means that you are not ensuring that you're going to count an object once and only once. Not only that, but that cell profile is going to have a bias depending upon the size of the object that you're looking for.
Okay, and keep in mind that if you come into your questions today, we're going to go through them and answer them, and please contact us to talk about today's topic, which is how do you decide which probe to use this for, more specific topics like how do we farm those probe and how much sampling do we use.
Yes, we have numerous webinars on our website already, and we're going to continue doing these, especially if you let us know if you like them, and feel free to offer up topics that you'd like us to address. The practical demonstration webinars cover how to implement optical fractionator in SafeVol, as well as Cavalieri and area fractionator. You can refer to the primary literature in order to see how researchers in your field are using stereology to obtain unbiased quantitative estimates of their feature of interest. And we also have how the methods were developed as references within our software, Stereology Investigator. If you'd like to learn more about Stereology Investigator or contact us with questions, you can contact us for a free trial, and you can also just let us give us feedback, let us know what you'd like to learn more about. Thanks for your attention.
Thank you very much. Good afternoon, and welcome to the SRS Image Stack Acquisition Webinar, MDF Biosciences' latest installment of our live web-based educational demonstrations. My name is Jose Maldonado. I'm a staff scientist and research liaison here at MDF Bioscience, and I will be leading this demonstration today. The goal of this webinar is to highlight the benefits, uses, and features of the SRS Image Stack Acquisition workflow, as well as to demonstrate its application. Broadly speaking, we will be considering the following today. What are SRS Image Stack series? Why would I want to use them? How do I generate a series of SRS Image Stacks using SRS Image Stack series workflow? Over the next hour, I will also take you through a step-by-step live demonstration on the use of SRS Image Stack series by workflow, with question areas throughout and after the live demonstration. For any questions not answered or addressed during our live demonstration, please visit our forum at forums.mdfbioscience.com. Alternatively, feel free to email us at info.mdfbioscience.com. Our demonstration must begin with a bit of background. The first question to address towards this end is simply, what is an image stack? Image stacks are high-resolution, disease-stacked images. The thin depth of field makes these images suitable for stereological analysis. In order to have these images be suitable for stereological analysis, means that we must acquire them with a high-power objective lens. Using an objective lens with a high numerical aperture means that very small increments can be used between each disease-stacked image. I'll have more on the use of high-powered objective lenses later in our demonstration. SRS Image Stack series, then, are a group of image stacks acquired in a systematic and random fashion and are suitable for stereological analysis. Image stacks are taken only where stereological probes will be placed. Image stacks can be analyzed offline on any Stereo Investigator workstation. Let me expand a little bit on the topic of systematic random sampling. Systematic random sampling involves having the user determine or define the distribution of stereological probes, or in this case image stacks, but not their location. This graphic shows the placement of acquisition sites, illustrated as small black line squares, and their systematic placement in reference to each other within the user-defined contour. SRS distribution of sampling locations will be varied from one acquisition run to another, as the software decides where to place these sites. Acquiring an SRS image stack means that image stacks will be acquired from random locations, but their position relative to each other will always be determined by the user. Acquiring an SRS image stack series requires specialized microscopy hardware. Very basic hardware requirements include a high-resolution digital camera, motorized stage capable of directing movements to X, Y, and Z axis, a computer running MDF software to drive all the motorized components of the microscope, and critically, high numerical aperture objectives. Let me expand on the topic of aperture and objectives a bit more. In order to discriminate one or multiple objects in tissue, we must use objectives with the ability to focus the very thin depth of field. To achieve this, we must use an objective lens with a high numerical aperture. Using a 60x or 100x foil objective is critical for stereological analysis, where the discrimination of two closely spaced objects is required. An objective lens with a numerical aperture of 1.0 or 1.4 will allow the user to make these types of discriminations. In summary, high resolution and a thin depth of field aid in the ability to discriminate using objects which may be practically on top of each other. So as a microscopist, why use SRS image stack series? Well, there are a number of reasons. Fluorescent markers may fade very quickly when observed at high magnification. Prolonged observation of thin depth of field focal planes is often required in stereological analysis. Many commonly used fluorophores may bleach quickly, and before analytical decisions can be made regarding the identity of single or covalent cells. And non-trivially, stereological analysis may in fact be time-consuming, making it difficult for labs to share microscopy resources efficiently. Image stacks, on the other hand, can be analyzed at the user's leisure without fear of signal degradation. Performing your stereological analysis on image stacks offline frees valuable microscopy hardware for other users or other analyses. SRS image stacks provide a digital record of tissue regions being sampled for stereological analysis. Also, the semi-automated hardware helps reduce user error over long acquisitions by engaging and disengaging appropriate hardware at the appropriate time. There are several reasons for using SRS image acquire stacks. So, what does the SRS image stack series acquire workflow do? Simply put, it makes acquiring SRS image stacks very easy. The SRS image stack series acquire workflow takes users through the process of acquiring image stack series from multi-channel or bright field stained tissue, which are suitable for offline stereological analysis. The workflow is formed as a step-by-step guide, helping users to do things such as trace the region of interest, empirically define the tissue thickness, define acquisition parameters, define stereological parameters, as well as saving these parameters for future use on other subjects in either the same experimental or control group. Before beginning any stereological analysis or image stack acquisition, users should have the following secured. Critically, sample tissue. The sample tissue must be free of all damage, including tears or missing tissue, and must always include the entire region of interest. The tissue, post-processing, should be thicker than the probe height plus the guard zone heights. Of critical importance is having your tissue stained thoroughly throughout the entire Z-axis. Stained tissue which has or lacks staining in the central portion of the Z-axis is not suitable for stereological analyses or SRS image stack acquisitions. Before beginning the SRS image stack acquisition workflow, users should also have such stereological parameters as counting frame, distribution, and counting frame size. Of course, calibrated stage hardware and software is important. By this we mean that your hardware should be calibrated both parcentrically and partlocally, and device command sequences should be delineated beforehand. Device command sequences are a series of commands which our software sends to the microscope hardware to initiate the movement and engagement of the specific hardware pieces at specific times. So for example, a device command sequence may open an excitation light shutter, engage a fluorescent cube, and set the camera's specific exposure settings. Of course, we recommend having the latest version of Stereo Investigator, which as of this transition is version 9.12. At this time, this is the end of our discussion of background topics. Please post any related questions you may have now before we begin our live demonstration of the SRS image stack acquisition workflow. So now, let's begin our live demonstration on how to acquire SRS image stack series using the SRS image stack series acquire workflow. In order to open the SRS acquire workflow, we must first have a live view, so then I will engage the camera by pressing the live view button, and also engage my DAPI fluorescent filter. Great. I'll use my video histogram to set my black and white points to try to obtain as optimal an image as possible. It is of some importance to not bleach your tissue while performing these types or these series of steps. So to this end, I will close my excitation light shutter until I'm ready to use my live image once again. The SRS image stack workflow is found under the acquisition menu, and it's found here, as you can see. As you can see, the workflow is broken up into 3 subtopics: areas to acquire, acquire configuration, and finally acquire. I will begin with areas to acquire. For areas to acquire, users will be prompted to enter subject information, set microscope to tracing magnification, and finally trace your region of interest. Go ahead and start that now. So for the purpose of this demonstration, I will enter my name, and I will choose a subject. The notes field is a useful place to enter notes regarding the subject or any other aspect of the sampling, which may be useful to you or other users later in the future. If this is not the first acquisition run that you are performing on a subject, then you may wish to load pre-existing stage sampling parameters. As this is our first demonstration, we will not use existing sampling parameters, but rather enter our own. The first step is to enter the number of sections which we wish to analyze. For this demonstration, we will be analyzing and we will be acquiring images from one tissue section. It is possible to acquire images or SRS image stacks from multiple contours, so long as they are on the same slide. This tissue was cut at 40 microns. The section cut thickness indicates or asks and requires not the post-processing tissue thickness which will be observed at a later step, but rather the cut thickness which your section device was set to. As we have only one section, we will leave our section evaluation interval as 1. If you have multiple sections, would require you to enter then your section evaluation interval, whether it be 1 or some greater value. So tracing magnification or step 2. Direct the user to set the microscope hardware to the low power objective that will be used for tracing. In this case, I will be using the 2.5 objective to trace the region of frame. Okay, I set my hardware to 2.5 objective lens and verified that I have the same lens file selected here in the drop-down menu. The next step is to trace my region of interest. For this, my first step will be to get a live view of my image. I'm choosing to use my DAPI channel because DAPI stain cells are the most numerous in this tissue and will give me the best chance at being able to delineate anatomical regions of interest. I will use my blue arrows to move my stage to find the edge which may be useful for me to begin my tracing. This is a good place. The serial section list lets me decide or select which tissue section I'm working on. If my slide contains more than one tissue section, and I wish to draw contours around more than one tissue section, I can select which section here. Alternatively, I have the option to add a new section or edit information about the current section. I will pick the appropriate name contour, and if I choose to, I can even change the color. I'll now begin my tracing. As you can see, clicking outside of the auto move box moves the stage and my contour drawings together in such a way that the relationship between the contour and the anatomy being delineated remains together. Right-clicking opens up a dialog box which allows you to select close contour, thereby closing the trace contour. I will now close my expectation line shutter to preserve my tissue. Now that we've gone through the first subtopic, please post your questions now on any topic related to entering name and subject information, adjusting microscope to tracing magnification, and creating a close contour around a region of interest. Shane has a question about how she can use pre-existing configurations. Let me go back to the workflow and show you how that will be done. One of the benefits of using the SRS image stack acquisition workflow is the ability to go back and forth between steps. Let me go back to step 1. If I did have a set of parameters I wish to use, I can simply click yes, and then navigate to wherever that file may be found. Here is the set of parameters that I saved from an earlier run. We will select no, and go back to step 3. Genevieve has a question that is the tracing evaluation interval entered in microns? I believe, Genevieve, what you're asking is related to the serial sections and the distribution from one to another. This is not entered in microns, this is entered in numbers of tissue sections. So if you had a series of tissue and you wish to analyze every 6th tissue section, then your tissue interval would be entered as such and not in microns. That's actually the fashion. Okay, Sebastian is asking about having multiple regions of interest in the same section. Well, Sebastian, the way that our software works is that we use specific contours for specific anatomical regions. To that end, if you wanted to, let's say, outline striatum, hippocampus, and cortex, all in the same tissue section, and acquire SRS image stacks that are going to be unique to each of those anatomical regions, what you do is you simply pick a different contour from the drop-down menu. So let's say that I wanted to trace striatum and hippocampus. After finishing tracing striatum, I would simply select hippocampus, return to my live view, move over to hippocampus, and then trace there. Okay, thank you for those questions. Let's move on now. The second subtopic in our acquisition workflow is the acquire configuration. This will help users configure microscope and software for acquiring SRS image stacks. It will help to empirically determine tissue thickness, select which contours we wish to be imaged if we delineate more than one contour per section, set probe dimensions, and specify SRS grid dimensions. Step 4, or set acquire magnification, directs the user to move to the objective lens which will be used for acquisition. As we mentioned before, it is critical to use a high-powered objective with a high numerical aperture. For this demonstration, I will be acquiring with a 100x oil objective, which I'm going to move to now. Clicking anywhere in the macro view with the left button will move the stage to that location. This may be useful if tracing edges need to be aligned with anatomy. To shift the region of interest, right-click the end-joint mode. Select the Align Tracing button. Click anywhere in the contour, and then click the location on the tissue where that position of the contour should be. One of the benefits of having semi-automated hardware is that it is possible to have hardware process here in software. For example here, the software process to finish adding oil or to change the version of oil before continuing. I'm now adding a bit of oil to my slide, and returning the stage to its working position. I use my video histogram to get an appropriate pixel citation, and then find my tissue I focus on. The software has kept track of the fact that I added a version of oil from a 63x objective, and so when moving to my 100x objective, no longer prompts me to do so. Fantastic. So you can see here that the software has detected that we are using the 100x objective lens, and has selected the appropriate lens file from the software. If your particular hardware does not have this type of communication ability, it is important to always manually drop down and select the appropriate lens. I'm going to go ahead and close my expectation lens shutter once again to preserve my tissue state. After we have set our microscope for acquisition power, we can hit next step. This step, or region selection, allows the user to select multiple regions if available to scan and acquire image stacks from. As we have selected only one region of interest, it is selected here. You can tell it is selected by the fact that it is bounded by this white box. If you had multiple regions, they would appear in this work area as well. It's possible to simply select all regions to have them all selected, or unselect all regions conversely. Once you've selected the regions of interest,